So we are going to start group 17 today. Okay, I've shared the notes in the WhatsApp groups. So you have all the notes and I'm going to just discuss it. So we will be finished. I think we will finish this chapter today only. Okay, so in group 17, we have fluorine, bromine, iodine, and astatine. It's start from group 2, 3, period 2, 3, 4, 5, 6. Okay, and when we talk about these elements, all of these elements are actually exist as a diatomic molecules. And here if you see, there are the colors that fluorine is either pale yellow or yellow. The chlorine is yellowish green, pale green. Bromine is red brown. Iodine is dark brown. Okay, I would prefer now don't use the dark brown. Note it down in your notebooks. It's better to write gray, black, or black instead of dark brown. Okay, just do keep this in mind. Now, not dark brown anymore. You have to remember it as a grayish black, gray black, or a black, and then the astatine, which is a black one. Okay. If we look at their states at the room temperature, the first two elements are the gases, which are fluorine and chlorine. The bromine is the liquid, and iodine and astatine are the solids. Okay. So again, remember, not dark brown; it's a gray black. So in iodine, so in a solid state, iodine is a grayish black, and when I heat it, it does not melt. Instead, it sublimes and turns into iodine vapors, and those iodine vapors are of purple color. So you are going to observe a purple fumes when you heat solid iodine. You are going to observe purple fumes. Is this understandable to everyone? And further, but iodine do exist in its aqueous form, which means it is soluble in water. So when it dissolves in water, have a red brown color. Okay, it have a red brown color. So iodine have interestingly three different colors in all three states. When it's a solid, it's a gray black or a black, not dark brown. I'm again telling every one of you that remember it's not dark brown, it's a gray black. Okay. When it turns into a gas, you are going to observe purple fumes. When it dissolved in water, you are going to observe red, brown, or a brown solution. Okay. Now, when we talk about astatine, the last one, it's a radioactive. So normally when we discuss the trends, we are not going to discuss astatine. Further, we call these group 17 elements halogen. Okay, we call these group 17 elements halogen. They exist as a diatomic elements, and when they form an ion, those ions are called halides. In those halides, they have a negative one charge, so they form ion by gaining the electron. So when they becomes ion, now we don't call it fluorine, chlorine, bromine, because when they have a negative charge, their suffix is replaced by IDE. So F negative ion is called fluoride, Cl negative is called chloride. In the same way, bromide, iodide, and astatite. So you must have to remember, if there is a written that it's a fluorine, then it means it's F2 molecule. And if it's a written, it's a the fluoride is written, then it means there is a F negative ion over there. And if it's written that fluorine atom, then you would consider as a single atom. But if just the name of the element is written, then it is always in a diatomic form. And if it's a ID in the end, then it's a negatively charged ion. Is this clear to everyone?
Yes.
Okay. Now have a look at their trends. in the properties, when we talk about the melting point and the boiling point of the group 7 elements, it increases down the group. We are observing over here, see, the first two are gases, then it is a liquid, and then the solid. So yes, the melting point is increasing down the group. And why is it so? That's what we have already discussed in bonding, that when we move down the group, the strength of the van der Waals forces or the intermolecular forces increases. And why it is increasing? Because the number of electrons are increasing. If you see, the atomic number of fluorine is 9. So in F2 molecule, there are only 18 electrons. If you look at chlorine, the atomic number is 17. So in Cl2 molecule, there are 34 electrons. In the same way, the atomic number of bromine is 35, if I am not wrong, I am not sure. So when it becomes bromine, it has 70 electrons. Right? So as the number of electrons are getting more and more in the molecules, the intermolecular forces or the van der Waals forces gets stronger, and as a result, the melting point increases down the group. Okay. And further, we are observing that there is a state change from a gas to a liquid and a liquid to a solid. And further, there is a trend in their color darker. Is this clear to everyone? Yes. Now, let's talk about the reactivity. When we talk about C, I'm saying halogen. So it means I am referring to the diatomic molecule. So when we consider these diatomic molecules, their reactivity decreases down the group. Okay, what happens to their reactivity? Their reactivity decreases down the group. Why? Because of this reason. If you see whether it's a fluorine or chlorine or any other halogen, when they react, during the reaction they gain electrons and becomes the negatively charged ion, right? So it means these atoms, the atoms of the group 17 tends to gain the electron, right? What they do, they tends to gain the electron. And when they gain electron, so if you see, if we look at fluorine is in second period. So if it's of that much size, then chlorine is in third period, so its size gets bigger. Bromine is in fourth period, even its size gets more bigger. So the bigger the size, the more it would have difficult to gain the electron from the outside, right? Because the nucleus in the center. So the force of attraction gets weaker to gain the electron, and that's why the reactivity decreases down the group. And further, the electronegativity is also decreasing. That's make these halogens less reactive when you move down the group. Is this clear to everyone? Yes, if anybody have any doubt, kindly ask. Okay, now think, when they are gaining the electron, these halogens, when we gain the electron in these halogens, the gain of electron is reduction, right? So the halogens undergo reduction, and if the halogen undergo reduction, then they considered as a oxidizing agent. Now think of a halide ion, whether it's a fluoride or chloride. When they undergo reaction, they react in the reverse way. So when the halide ion react, they tends to lose electron and becomes the halogen again. So that loss of electron is considered as oxidation. So if we move down the group, the reactivity of these halide ions increases. Why? The same reason. Because the halide ions have to lose the electron, right? So the bigger the size, it's more easier to lose the electron, because the valence electron is further away from the nucleus. So it can be easily, removed. So now we have to remember these two things. When we talk about the reactivity of a halogens, their reactivity decreases down the group. Why? Because down the group the electronegativity decreases, and there is a lesser nuclear attraction to gain the electron. When we relate the halide ions down the group, we can say the reactivity of halide ions increases down the group because halide ions tends to lose electron. So as the size gets bigger, it's easier to remove the electron because the valence electron is away from the nucleus. Yes, is this understandable to everyone? Abdullah, Dawood, Shariar, Tayyab, Ubaid, Wariza, Amna, Alia, Parishay, Simra. If anybody have any doubt, kindly ask. Okay. Now, see this. This is a fluorine, a halogen, and this is the iodine. So when we consider their reactivity, we consider the fluorine is the most reactive one and iodine is the least reactive one. So it means that the fluorine is the strongest oxidizing agent among all the halogens, and iodine is the weakest oxidizing agent among all the halogens. Now let's talk about halides. When we consider these halides, then this iodide is the most reactive and the fluoride is the least reactive. So iodide is the strongest reducing agent and fluoride is the weakest reducing agent. Is this clear to everyone?
Yes.
Yes. If anybody have any doubt, kindly ask. Okay, now let's, after this, we have the reactions. So first, the reactions of halogens with the hydrogen. So when they react with the hydrogen, they would form hydrogen halide. So when fluorine reacts with hydrogen, it would form hydrogen fluoride. See, as fluorine is the most reactive one, so the reaction is occur at room temperature. Chlorine becomes less reactive, so we need a light for a reaction to occur, and the hydrogen chloride is formed. Bromine even gets its reactivity is even lower than the fluorine, so we need a heat. The triangle sign on the equation always show that there is a heating, so we need a heat energy for this reaction to occur, and hydrogen bromide is formed. Then with the iodine, along with the heating, the reaction is not goes to the completion. Instead, the equilibrium is established, which is showing that all of the iodine is not converting into hydrogen iodide, which indicates that it is even less reactive than this bromine. Because even bromine needs the heating, but the reaction is going towards the completion. All of the bromine is converting into hydrogen bromide. But this reversible sign over here shows that all of the iodine is not converted into hydrogen iodide. Is this clear to everyone?
Yes.
Okay. Now, the other thing that what we have already discussed in the bonding as well, when we talk about HF, hydrogen fluoride, the hydrogen is bonded to the fluorine. So here, between the hydrogen fluoride molecules, there is a hydrogen bond. But here, in this case, there are weak intermolecular forces or a permanent dipole-dipole forces. But when we move from HCl to HBr and HBr to HI, the number of electrons increases, and all these three compounds have a same kind of forces. So the strength of these forces getting stronger from HCl to HBr and HBr to HI, and due to which their melting point increases because the electrons are increasing. That's why they are getting stronger. But these are weaker than the hydrogen bonding. So here you have a graph showing the melting point on the left side, where it indicates the melting point of HF is highest among all these because of hydrogen bond, and the melting point of these are the lower because of the permanent dipole-dipole forces, which are weaker. But the melting point is increasing from HCl to HI is due to the increase in the strength of the intermolecular forces as the number of electrons are increasing. Is this understandable to everyone? Yes, if anybody have any doubt, do ask. Okay. Then the thermal decomposition of hydrogen halides. See, the fluorine is, for example, if fluorine have a this size, then chlorine must be bigger than this. Bromine is even more bigger, and iodine is even more bigger. So when the hydrogen bonds with them, the distance between the hydrogen and the nucleus increases down the group, right? Because if the size of a group 17 element is getting bigger, so the distance between the nuclei of the hydrogen and the nuclei of the group 17 gets bigger. So as a result, what would happen? If you see over here, the bond length is increasing. Is this understandable? Yes? Yes, the online students, if anybody have any doubt, kindly ask. Yes, Alia, Amna, Parishe, Ravisa, Variza, Tayyab, Ubaid.
Yes, sir.
Simra, Sharia, Abdullah.
Clear.
So the bigger the bond, the more weaker it is. So here we have a two experiments to show this. In one test tube we have a hydrogen bromide, and in the other test tube we have a hydrogen iodide. So what we did, we put a hot glass rod in both the test tubes. Where there is an HBr, there is no observation. For example, its bond is of that length, for example. But here in HI, the bond length is bigger because the iodine is bigger. So what would happen as we put the hot glass rod, we are observing the purple fumes, which is indicating that this hydrogen iodide is decomposed to form hydrogen and iodine. So as soon as the iodine is formed, you are observing the purple fumes. So as we move down the group, the bond of the hydrogen halide gets weaker because the atomic radius is increasing and the distance between the two nuclei is increasing. Is this clear? So it gets easily broken down if there is a bond between hydrogen iodide as compared with the rest of the hydrogen halides which are above this iodide. If anybody have any confusion, do ask. Okay, so it means among these, the bond between hydrogen and fluorine is the strongest, and the bond between hydrogen and iodide is the weakest. Okay, so now what would happen when I put these in water? They are going to dissolve. And why they are going to dissolve? Because they are broken down into ions. Okay, so see, we just discussed that HF is the bond between the hydrogen and fluorine is weakest. Oh, sorry, strongest. So it is going to break down partially, which means some of the HF molecules breaks down into hydrogen and fluoride ions, and rest of the molecules stays as a molecule. That's why it shows least acidic behavior in water because its bond is strong. Then the bond between a hydrogen and chlorine is weaker. So it gets readily broken down into water, forming hydrogen ions and chloride ions. So that's why we know that HCl is a strong acid, right? So when we comes to HBr, the bond is even breaker. The bond between hydrogen and bromine is even weaker than the hydrogen and chlorine. So it means the HBr is even more stronger than HCl. It dissociates more readily to gives you hydrogen and bromide ions. And when we comes to HI, this bond is even more weaker. So it would produce hydrogen ions and iodide ion most readily among these, which makes it the strongest acid among these or the most acidic among these. And this one is the weakest acid among these or the least acidic among these. Is this clear? Yes, if anyone have any confusion, do ask. So that the reason is the same, that strength of the acid increases down the group because what we observed that down the group bond length is increasing, due to which bond gets weaker, and hence if bonds get weaker, so it can easily broken down and easily donates the hydrogen ion, the proton. Yes, is this clear to everyone? If anyone have any confusion, do ask. Okay. Next, we have a precipitation reaction. So, if you recall, precipitation reactions are the ones where the two solutions are mixed. It means we have a two soluble substances and we made their solutions and we mix these two solutions. And on mixing of these two solutions, we get one insoluble substance. Then that reaction is called precipitation because on mixing of those two liquids, there is a solid forming in the solution, and that's why we call it precipitation. And the solid particles that are formed in the reaction mixer are called precipitate. Is this understandable to everyone? Yes, if anybody have any doubt, kindly ask. Okay. So most of the time examiner asks you to write the ionic equation, sometimes for acid-base reactions and sometimes for these precipitation reactions. So in those precipitation reactions or whether the any other reaction where we have to write the ionic equation, first what we have to do, we have to figure out the spectator ion. And what are the spectator ions? When you split the equation into ions, you can figure out there are some ions, specific ions, which are unchanged. On the reactant side, they have a same charge and they have a same state, and in the product side, they have still same charge and the same state. So we call those ions the spectator ions. So if we remove these spectator ions from the equation and then write the rest of the equation, so the equation becomes ionic equation. So that is the simple rule that you have to remove the spectator ions from the chemical equation. The leftover equation is ionic equation. Okay. So then you have to remember this. Whenever you are going to split the substances in the chemical equation into ions, you make sure that if there is a water, carbon dioxide, any element, any substance present in a solid state, any precipitate or any gas, we do not break them into ions. We only break the substances into ions which are actually aqueous. Okay, the substances which are present in the, and even not just substances, I think more preferably the compounds which are in the aqueous state are broken down into ions, and then we have to figure out which ion is the spectator ion. Beside the aqueous compounds, whether the compound is in their solid state, whether there is an element, whether there is a gas, we do not split it into ions. We split only the compounds into ions which are in the aqueous state. Is this clear? Okay. Now we are discussing group 17 elements. So if we look into group 17 elements compounds, so if silver forms a compound with a chloride or bromide or iodide. In the same way, if lead forms a compound with a chloride, with a bromide, and with a iodide, all these compounds are water insoluble. So it means if in a reaction they are forming, they form a precipitate, and those reactions are considered as precipitation. Is this clear? Yes. If anybody have any doubt, kindly ask. Now, you have to remember this. Whether it's a silver chloride or lead chloride, you are going to observe a white precipitates. If there is a silver bromide or a lead bromide, you are going to observe a green precipitates. Whether there is a silver iodide or lead iodide, you are going to observe a yellow precipitate. Till here, it's clear to everyone?
जी sir.
Okay. Just give me a minute, please. Okay, so see over here, we have a silver nitrate. If you recall, all nitrates are water soluble. So when silver nitrate reacts with a sodium chloride, both are aqueous, so their ions exchange, and as a result, silver chloride is formed and sodium nitrate. So silver chloride is water insoluble, so it would make a white precipitates in the solution and becomes just insoluble. So if I have to write the ionic equation, first I have to split the chemical equation into ions. So it's an aqueous compound, so I have split it into two ions. This one is an aqueous compound. I will split it into two ions as well. This is a solid. So I keep it as it is. There is no need to split it. That's what I have discussed with you, that if it's a solid, there is no need to split. This one is an aqueous. So I will split it into a ions as well. Now if you see, there is a sodium ion which is present on both sides, right? And there is a nitrate ion which is also present on the both sides. The silver ion is here, but the silver ion is not present on the product side. Instead, it becomes the part of the solid. And in the same way, there is a chloride ion in the aqueous state, which also becomes the part of the solid. So the ions which are aqueous on both the sides, these are considered as the spectator ions, and we remove these ions, and the rest of the thing that is left, we write them, and that is our ionic equation. So that's how we write the ionic equation. Is this understandable?
Yes, sir.
If anybody have any doubt, kindly ask. Okay. Now, what would happen then? We got a white precipitate of silver chloride. When we add either dilute or concentrated aqueous ammonia in these white precipitates, these white precipitate dissolves, which confirms that there is a chloride ion present. Because if you are just getting a white precipitate, there might be a possibility that you are mixing the color of white or a cream, because these colors are very close to each other. So by just looking, if you have only one test tube and the precipitates are formed, so sometimes it would become difficult to identify whether that precipitates are the white precipitates or whether that precipitates are the cream precipitates. So what we would do for this, we would add either dilute or concentrated ammonia in it. So on adding dilute or concentrated ammonia, if the precipitates get dissolved, then it assures us that there is a chloride in the solution, and that they get dissolved by this reaction. Actually, when we add aqueous ammonia, reaction occurs, and as a result, the precipitate gets dissolved. Is this clear to everyone? Just if anybody have any doubt, do ask. Okay, so in the same way, now I have written the ionic equation only when we mix actually silver nitrate with, for example, sodium bromide. Instead of NaCl, NaBr, I would get a AgBr, and it would form a precipitate of a cream color and sodium nitrate. So the ionic equation would be same as this one, because the rest of the ions are the spectator ions, and there is a cream precipitate. So if I have to confirm that whether that are actually the cream precipitates or not, so we can do these two things. If I add dilute ammonia, so the precipitate dissolves partially, which means you can figure it out by the height, whatever the height of the precipitates. After adding the dilute ammonia, there are only some precipitates left. So it means that the precipitates were a cream precipitates, and it's a bromide ion over there. That shows the conformation of the bromide ion. And because when we add a dilute ammonia, and if there are a chloride and there are exactly the white precipitate, then all the precipitates get dissolved. And when we add a concentrated ammonia, then the precipitates actually dissolves completely. So the dilute ammonia with the chloride and dilute ammonia with a bromide will actually help me to figure it out whether the ion, the halide ion that is present in the sample is a chloride or a bromide. If there is a chloride, then with dilute ammonia it is completely dissolved. But if there are clean precipitates, then they are going to dissolve partially. And how we would observe this? By observing that there is a decrease in the height of the precipitates, but all the precipitates are not completely dissolved. And the same reaction would occur when we add aqueous ammonia. Is this clear to everyone? Now afterwards, iodide. In iodide, there is the same thing. We are using silver nitrate and sodium iodide. So yellow precipitate of silver iodide is formed. Here I've just written the ionic equation. So if we add aqueous ammonia in it, whether concentrated and diluted, precipitate remains insoluble. There is no dissolving of the precipitate, which is showing that there is a iodide ion. So from here we got a one trend over here that the silver halides of the group 8, the silver halides, their solubility decrease in aqueous ammonia decreases down the group. Because chloride is dissolving completely, bromide is dissolving partially, and the iodide is not dissolving. So the solubility of silver halides in aqueous ammonia is decreasing down the group. So we got this trend over here. Is it clear to everyone? Yes, Abdullah, Dawood, Shahriar, Tayyab, Alia, Parishe, Rabisa, Simra, Waliza.
Yes, sir.
Okay. Now, the displacement reaction. This reaction is the one which you have already studied in your IGCSEs and O levels. We know that down the group the reactivity decreases. So the more reactive halogen is there, if the more reactive halogen is there, then it can displaces the halide of the less reactive halogen. But here if you see the chlorine, there is a chloride and a bromine. So if you see, this chloride is of a more reactive halogen, that's why no reaction occurs. But if we have a negative ion of halogen, the less reactive halide forming a halogen, the less reactive halide turns into a halogen, and the more reactive halogen turns into a halide. Is this understandable? Yes. So just recall,
Yes, sir.
see, if you see over here, if I write the elements in the way that they are in the periodic table, so this one is the most reactive and this one is the least reactive. So obviously, if it's a fluoride is over there, so whether I use chlorine, bromine, or iodine, no reaction would occur because it is the most reactive one. But if I use fluorine with either potassium chloride, potassium bromide, or potassium iodide, fluorine can displace all of them because it is the most reactive. In the same way, for example, okay, here if I have an iodide, for example, so iodide is the least reactive one from the group. So whether I can use bromine, chlorine, or bromine or fluorine, iodide can be displaced. Yeah. Yes. It's 2 NaF. So if you look fluorine, chlorine, bromine, iodine, and astatine. So this one is the least reactive one. So that's why fluorine can easily displace it to form sodium fluoride, and we get astatine as a halogen. But if you see the second last equation where we have a fluorine as an halide fluoride, and we are adding chlorine. So chlorine is less reactive than the fluorine. So chlorine cannot displace its halide ion, its fluoride ion, and here no reaction would occur. Yes, if anybody have any confusion, do ask. Otherwise, I will be proceeding to the next subtopic. Is this clear to everyone?
Yes.
Okay, then this one is a little trickier. We are going to discuss the reactions of these halides with the sulfuric acid. Okay, so if you look over here in the first equation, I am using sodium chloride with the sulfuric acid. So do remember, whether I use sodium chloride, whether I use magnesium chloride, whether I use potassium chloride, it doesn't matter. The important thing is that chloride ion present over here with a -1 charge. So whatever the compound is there, the ionic compound, and it have a chloride. So what would happen? The sulfuric acid would react with it, and as a result, what we will going to get? We will going to get a HCl and a salt. So in the first equation, you can make this as your products or this as your product. Both are considered as correct because in both the cases we are getting HCl. In the first products that I would form is the one where 1 mole of NaCl is reacting with sulfuric acid. So there is 1 sodium, so it displaces only 1 hydrogen from the sulfuric acid. For the second one, I have to balance this equation by 2. If I put a 2 over here, then I can make the product in this way, right? And if I didn't put a 2 over here, then I don't do this thing, then I would show the product in this way only. But if I put 2 over here, then instead this, I would show a product in this way. So there will be 2 HCl as well. Is this understandable? So see, the common thing is that whether it's a magnesium chloride or sodium chloride, in any case, the one product is common, that is HCl. So actually what happens that this HCl is formed in a very excess amounts. Okay. Now, when instead this, now for example, we have a bromide, sodium bromide or magnesium bromide. Here, nothing in the case of chloride, nothing else is happening. Only HCl is formed, and due to the formation of that HCl, we are going to observe the steamy fumes. But in this case, when there is a sodium bromide, first we get the HBr in the similar way that HCl is forming in the previous reaction. But this HBr again reacts with the sulfuric acid, and when this reaction occurs, if you see in this reaction, there is a change in oxidation states of the element. See here, bromide is Br with a -1 charge. When it turns into HBr, it still remains as a -1 charge. Okay, so this the first reaction is considered as an acid-base reaction only. Okay, that is the same reaction that occurs with the NaCl or MgCl2. But when HBr is formed, HBr reacts with the sulfuric acid, and in this second reaction, we would observe a change in the oxidation numbers. So we call this reaction a redox reaction. So see, here there is a bromine with a -1 charge, but here we got a Br2, which means its oxidation number is changes to 0. So what it indicates that there is a loss of electron, which means loss of electron means that it's an oxidation. And if it's an oxidation, so it means it's a reducing agent, and that's what we have discussed in the started, that the halide ions are the reducing agents. And if you see over here to the sulfur, its oxidation number is +6. And when it turns into sulfur dioxide, its oxidation number becomes +4, which indicates that it gains 2 electrons, which means it undergo reduction, which means sulfuric acid is behaving as an oxidizing agent over here. First, tell me, is this understandable to everyone? The comparison between the reaction of sodium chloride with the sulfuric acid and the reaction of sodium bromide with the sulfuric acid. Yes, Abdullah, is it clear?
Yes, sir.
Alia and Parisha, is it clear?
Yes, sir.
Yes, Parisha.
Yes, sir.
Rabisa and Shahryar, is this clear?
Yes, sir.
Yes.
Simra and Tayyab?
Yes, sir.
Yes, Tayyab. Bariza?
Yes, sir.
Okay, so what I can conclude from this before going to the next one, it means that HCl can also behave as a reducing agent, but HCl is not a strong enough reducing agent to reduce the sulfuric acid. But hydrogen bromide is a strong enough reducing agent that it can reduce the sulfuric acid. That is the one aspect. The other aspect is that sulfuric acid is behaving as an oxidizing agent. So it means we can conclude that sulfuric acid is not a strong enough oxidizing agent that it can oxidize chloride, but it is strong enough to oxidize bromide. So in both way we can relate. When we make sulfuric acid as a subject, we can say it is not that much strong that it can oxidize a chloride to a chlorine, but it is strong enough that it can oxidize bromide into a bromine. But when we make the halide ions a subject, we can say chloride is a reducing agent. That's why it cannot able to reduce sulfuric acid, and bromide is stronger reducing agent than the chloride. That's why it reduces sulfuric acid. Is this clear? Yes, is this point is clear to everyone? Okay, now see, here sulfuric acid, the sulfur is reduced by just gain of 2 electrons, right? And as the bromine is formed, so we are going to observe the red brown fumes. Okay, now have a look over here. When sodium iodide reacts with the sulfuric acid, hydrogen iodide will form. This hydrogen iodide reacts with sulfuric acid in 3 different ways. We just discussed initially that down, when we move down the group, the reducing ability of the halide ions increases. They get stronger reducing agent. So see that it is that much stronger that it, in the first case, it can make sulfur to gain how much electrons? 2 electrons. In the second case, it makes one sulfur to gain 6 electrons, and in the third case, it makes sulfur to gain 8 electrons. So see how strong enough that iodide ion is. So that is the proof that we discussed the trend initially, that down the group, the halide ion gets more stronger reducing agent. So hydrogen iodide is even more stronger than the HBr. That's why it is making the sulfur to gain even 8 electrons. But bromide ion just makes sulfur to gain only 2 electrons, not more than that. There is no other reaction. But Hi can react with the sulfur in all these 3 ways. So examiner can ask any one of these equations. So you have to remember, if the examiner would give you, for example, this observation that you are observing only purple fumes with a reaction of HI. So it means you have to write this equation. But when the sulfur is forming, the sulfur is a yellow solid. So examiner gives you this example, this observation that the yellow solid is observed, then you have to write this equation only. And if the examiner told you that there is a purple fuse, that the purple fuse is the common thing that is going to observe in any of these cases. But when the H2S is formed, it is also a gas and it have a strong smell of a bad eggs or a rotten eggs. So if examiner gives you this observation, then you have to write only this equation. Is this clear to everyone? Yes. And that's what we have discussed is written over here. So you can go through this as well. Let's see that HI is the strongest reducing agent than HBr. That's why it can reduce sulfur from +1 to -2. That would the last case where H2S is forming. But bromide can reduces sulfur from +6 to +4 only. And sulfuric acid can oxidize iodide to iodine and bromide to bromine, but it cannot oxidize chloride. That's what we have discussed, because it is not that much strong oxidizing agent that it can oxidize chloride, but it is strong enough to oxidize bromide and iodide. Is this understandable to everyone? Now, let's have a look at phosphoric acid. So, when we do the reaction with the phosphoric acid, the same thing happens and hydrogen iodide is formed. But afterwards, there is no reaction take place. So, it means it is a very weak oxidizing agent that it cannot even oxidizes the iodide, the I with the -1 charge. Yes, is this clear? Abdullah, Shahryar, Tayyab,
Yes, sir.
Alia, Parishe, Rabisa, Simra, Variza.
Yes, sir.
Okay. Now the next reaction is disproportionation reaction. We already have discussed this reaction in redox. So disproportionation reaction is the one in which a single element or a single species undergo both oxidation and reduction. So see, there are three kinds of disproportionation reactions of the halogens. When we add cold dilute sodium hydroxide at 1500 degrees Celsius, then the chlorine reacts with NaOH, forming NaCl and NaClO. If you see here, the oxidation number of chlorine is 0. In NaCl, it becomes -1, and in NaClO, it becomes +1. So out of these two chlorine, one chlorine is reduced, and one chlorine is oxidized. That you see this. So -1, -1, and -1, and here you have the ion equation in the green. When we use hot concentrated NaOH at 70 degrees Celsius, yes, the previous one, then we got NaClO3 instead of NaClO. And in NaClO3, chlorine have a +5 oxidation number from 0. So see, chlorine is changing from 0 to -1 as well as +5. So chlorine is undergoing oxidation and chlorine is undergoing reduction as well. So that's why it's a disproportionation reaction as well. And again, what we did, we figure out the spectator ions and cancel them out. The rest of the equation would be the ionic one. So examiner asks you both the equations. It's up to examiner. Sometimes they ask you to write the ionic equation. So you have to write this one then. The one written in the green. Is this clear? Now, the third reaction is the reaction of chlorine with water. So when we add a chlorine in water, Again, a disproportionation reaction occur. We get two products of chlorine. One is HCl and one is HClO. In HCl, chlorine is turning in from 0 to -1, which means a reduction. And in HClO, chlorine is turning from 0 to +1, which means an oxidation. And due to this HClO, chlorine acts as a bleaching agent. Okay, and it turns why it acts as a bleaching agent, because it in the presence of sunlight, this HClO decomposes to form HCl, and this atomic oxygen which undergo oxidation and which actually kills the microbes. And due to this, it is considered as this HClO is chloric acid is considered as an oxidizing agent as well. Okay, this is an oxidizing agent as well. Is this clear to everyone till here? Okay, now we are left with the uses. So you must remember the uses of these halogens. For example, when we talk about CFCs, they are used to form chlorofluorocarbons and they are used in toothpaste. Chlorine is used in normally to treat water in the swimming pools. Bromine is used in insecticides and further as a flame retardant agents. And iodine is used as a disinfectant. So here the group 17 is ended. Okay, so today we don't have a fast paper session, but tomorrow inshallah. Okay.
सर आपने
Okay, so take care everyone.
ऑर्गेनिक केमिस्ट्री के बाद रिकॉर्डिंग अपलोड करी है?
1 minute. Yes, what were you saying?
आपने ऑर्गेनिक केमिस्ट्री के बाद मास स्पेक्ट्रोमेट्री के बाद फिर रिकॉर्डिंग्स अपलोड करी हैं जो आगे कर रहा है?
मैं चेक करूंगा, मुझे याद नहीं हुआ तो मैं कर दूंगा।
YouTube पे डालेंगे?
अल्लाह हाफ़िज़। हाँ, YouTube पे डालनी है और मैं फर्दर डाल दूंगा।
सर थैंक यू। अल्लाह हाफ़िज़।
Okay, take care everyone. अल्लाह हाफ़िज़।